So last time we focused on beta decay, and this time it is the turn of gamma decay. So for this tutorial, I've chosen to use an atom of beryllium as our start point, just to change it up a little bit. So we've got an atom of beryllium, and the mass number, the A, tells us that there are 9 particles in the nucleus of a beryllium atom, and the atomic number down here, the Z, is 4, and that tells us that of those 9 particles in the nucleus, 4 are positive protons. So let's have a look at the picture of that. So here we've got our nucleus of beryllium. There are 9 particles, 1, 2, 3, 4, 5, 6, 7, 8, 9. And 4 of them are protons. 1, 2, 3, 4, coloured in red with their little positive symbol. Now, at the moment, this nucleus of beryllium is unstable. Remember, that means that the strong nuclear force that holds all of these particles together isn't quite strong enough to overcome the fact that these protons want to repel each other and push away. So we've got an unstable nucleus. However, this nucleus doesn't want to be unstable. It wants to be nice and happy and stable. Of the different options that particles with an unstable nucleus have, is they can give out a gamma wave. So previously we've looked at when alpha particles were removed, those 2 protons and 2 neutrons. When a beta particle was removed, that was our last video, where that little high energy electron was removed. This time we're focusing on gamma, and a gamma wave, as we can see here, is emitted from our nucleus. Remember, emitted means to give out or to kick out. So our unstable nucleus kicks out a gamma wave, and we'll write that on here. And remember from the previous unit that a gamma wave is a high energy electromagnetic wave, and it's got a really high frequency, and we can see that because there are very many waves that are all in the same time period, in the same second, and we can see that that wavelength is really short. So this tells us we're dealing with a gamma wave. Now you will also be able to tell here that no other particles have been removed from this nucleus. It's just the wave that has been kicked out. So when we follow this through from beginning to be unstable, we remove the gamma wave, we end up with something that is nice and stable over here. And let's have a look what we've been left with then. So we've got a nucleus with, let's count up the particles. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And that is the exact same as what we started with. So we started with 9 subatomic particles in the nucleus here, and we've still got 9 because no particles have been removed, just a wave. So we've still got 9 subatomic particles. Let's count the protons. 1, 2, 3, 4. We've still got 4 protons. So in fact, we can see that the A, the mass number, has not changed, and the Z, the atomic number, has not changed. So we have still got ourselves an atom of beryllium. It's the same thing. It's now just more stable because it has kicked out, it's removed a gamma wave. So if we turn that into the equations, this one's nice and easy. So we start with our unstable, remind ourselves, we'll put that on. We start out with our unstable beryllium atom, and we remove a gamma wave, and we write gamma like this. It's this funny looking Y, and waves have no mass, so we have a 0 for the mass, and they have no charge either. They're waves, they don't have a charge, so gamma 0, 0. And we know that we were left with something that had 9 subatomic particles in the nucleus, and 4 of them were protons, the 9 and the 4. So we know that we've got to leave that as a Be for beryllium. Same thing, just more stable. So when we drop down here onto the general equation, we always have the X to represent the unstable atom, or the unstable nucleus, with A for mass number and Z for atomic number. We kick out, or we emit, the gamma wave with no mass and no charge, because it's a wave, it doesn't have those types of properties. And now we can see that because nothing has been removed from the nucleus, A stays the same. Well, a wave has been removed from the nucleus, but no particles have. And the number of protons is the same. 4 of those particles are protons. So Z, the atomic number, has not changed. So we'll leave Z as Z. And because A, and particularly Z, has not changed down here, we can know that the atom still has the same identity as it started with. So in the example, it started as beryllium and ended as beryllium. So we use, in the general terms, it started as X and it ends as X, where it's now nice and stable. And that is gamma decay.